Another thing that momentum lets us do is deal with the fact that we've sort of been cheating a little bit. When we talk about a car or a box or anything like that, we talk about a car as if it's located at one point. Well, the car has a lot of mass. There are moving parts, right? And so we want to talk about sort of the center of this mass. And then we can see where forces act or momentum changes happen, things like that. So we can move away from treating objects as just point particles and talk about them actually having size and dimension, which is more realistic. And so we're going to talk about the center of mass of an object. And this is a weighted average. You know what a weighted average is, right? You take into account the fact that a test is worth 2 or 3 times some other object towards your grade, and so you have to throw that extra weight in, like how much more is it weighted? Well, we can do the same thing in terms of our mass to find out where is most of the mass located. So instead of something complicated like a car, we'll start with 3 objects. Like if I have an object that's fairly big, a small, and a small object here, the center of mass of a sphere would be right in the middle. That's sort of the central. So that would be the center of mass of each of the objects. But then if I wanted the center of mass of this system, then I would say it's somewhere a little off from center, sort of along the line, if these two are the same size, if they're the same mass. So somewhere like right there might be my center of mass. All right, so right here, maybe X marks the spot, just a little bit off from the center, because most of the mass is really concentrated in this larger object, but these two sort of pull the center away towards their side, okay? So this is a weighted average given mathematically by the position of the center of mass is equal to the position of each object times its mass. It's weighted by its mass. So if this is mass 1, 2, and 3, we would say, well, where mass 1 is times its mass plus mass 2 times its mass plus mass 3 location times its mass, all divided by the total mass of the system. In other words, M1 plus M2 plus M3. That's how we do a weighted average. We just put the weights in front of whatever it is we're trying to find the weighted average location of the center of this. So we can rewrite this as our mass total. If we know the position, we can find the velocity, right? Because the velocity of the center of mass is just the derivative with respect to time, and that means we take the derivative of each of these terms. I mean, this is a constant that we can pull out, right? So VCM, this mass just stays down there. It doesn't change with time. That's our mass total, right? And then we can do a term-by-term derivative. So an M1 times derivative of R1 with respect to t, which would be a V1, plus M2 times the derivative of R2, M2, so that's VT. Derivative of R2 with respect to time is V, plus M3, V3. And now this is starting to look, I think, a little familiar, this M1, M1V, all of those things. If I multiply this M over here, I get M total times V center of mass. If we look at this, this is the momentum of 1 plus the momentum of 2 plus the momentum of 3, okay? So what we have is this, the total mass times the velocity of the center of mass is the total momentum, right? Because it's the momentum of 1, 2, and 3, or 4, 5, and 6, however many more we've got. We can put a plus ... there, okay? So the total momentum is equal to the total mass times the velocity of the center of mass. And so what that says, if we go back over to our equation, Newton's second law, sum of the forces is equal to change in momentum with respect to time, then we can say, hey, the sum of the external forces on an object, right, is equal to then the momentum total of whatever we've decided is our system, dt. And so that, of course, if this is 0, the total momentum stays fixed. But even if it's not 0, we can say, hey, this acts on the center of mass. It's as if it acts on the center of mass. So when we know where the center of mass is, say it's there for a car, that's a little high for a car. It's not a great car drawing anyway, but it's somewhere like that. It's okay to draw, hey, that's effectively where my mg acts. It's as if all of the mass of the car is centered right there, and that's where the force acts, because that is where we get this change in momentum. Now, certainly, if a car, let's hope it's not a car, but if it's some object that's rotating, what that means is that it will, in free space, it will rotate about its center of mass. So if you have something that you throw in the air and it's twisted, like this marker is twisted, what happens is its trajectory will go like this, and that will be on the center of mass right there. But as it flips over, so if it's flipping over, then it's still, that center of mass follows the parabola, and it continues to flip over along the center of mass. So these other parts continue moving relative to the center of mass, but we can still use all of the equations we've been using in our setups, our force diagram, if we focus them at the center of mass, which is really convenient to be able to do. So it's useful to know where the center of mass is, because then we can keep everything we've done before. So that's good news, that we don't have to just throw it away.